Recognizing series combinations of resistors allowed us to reduce the number of unknowns in our circuit. Likewise, parallel combinations of resistors can also reduce the number of unknowns in our circuit. First, we need to define what we mean by parallel elements. By definition, parallel elements share exactly the same voltage difference at all times. Here's a set of two parallel elements. I've defined the voltage V1 across this element and V2 across this element. If we apply Kirchhoff's voltage law around this loop, we find that minus V1 plus V2 is equal to 0. If we take V1 over to the other side, we find that V1 is equal to V2 all the time. Another way to identify parallel elements is if several elements share the same two nodes. However, if you're in any doubt as to whether two elements are in parallel, apply KVL around the loop. If you encounter more than one element in that loop, those elements are not in parallel. Let's take a look at an example circuit and identify parallel circuit elements. If I do KVL around this loop, I encounter three elements. It looks like none of those are going to be in parallel, but I can check this by defining voltages, V1 and V2, across these elements and doing KVL. So negative V1 plus V2 plus 5 volts is equal to 0. So none of these are necessarily the same. Now let's look at this loop over here. If I do KVL around this loop, I also encounter three elements. So it doesn't look like any of those are going to be in parallel. Let's call this V3 and this V4 and do KVL to double check that. I don't know what the voltage is across a current source. So I'm going to define a voltage, V sub S there, and now negative V3 plus V4 minus Vs is equal to 0, and none of those are necessarily the same. The only two that are in parallel are these two. If I loop here, I only encounter two elements, and V3 is equal to 5 volts all the time. Now let's specifically look at parallel combinations of resistors. These two resistors are in parallel. If we do KVL around this loop and KVL around this loop, we see that both of the resistor voltages are the same, and they're both the same as this voltage difference V. The total current through both resistors is I. As always with passive elements, we followed the passive sign convention when defining V and I. Next, I'll define I1 and I2 as the currents through the individual resistors and determine a relationship between V and I for this pair of resistors. That'll give us an IV characteristic for the whole circuit to the right of these terminals. So, KCL up here tells us that I is equal to I1 plus I2. The voltage across R1 is V, so I1, according to Ohm's law, is V over R1. Likewise, the current I2 is V over R2. So I is equal to V times 1 over R1 plus 1 over R2. If I divide both sides by I and by this term, I get V over I is equal to 1 over R1 plus 1 over R2. That's a voltage-current relationship at these terminals. I can change this around a little bit just by multiplying it times R1 over R1 R2 over R1 R2. I can multiply anything by 1. So this can also be written as V over I is equal to R1 R2 over R1 R2 divided by R2 is R1 plus this divided by R1 is R2. These two are equivalent expressions. Both of these look like a resistance. If I call this Req and replace these with a single resistor, V divided by I is equal to Req. So if Req is equal to this or this, these circuits are exactly the same. So the circuit on the left is mathematically equivalent to the circuit on the right based on the voltage-current relationships at their terminals. If Req is equal to 1 over the inverse of R1 plus the inverse of R2, because anything we connect to these terminals won't know the difference between these two circuits. For this special case of two and only two resistors, this equation is equal to the product of the two resistances divided by the sum of the two resistances. As with series resistors, notice that we're not planning to change the physical circuit so that it has only one resistor. But when we analyze the circuit to predict voltages and currents, we can make the replacement and analyze the simpler circuit to predict how the original circuit will behave. We can generalize this result for an arbitrary number of parallel resistors. Suppose we have n resistors, all in parallel. The resistors are R1, R2, up to Rn. If we do KVL around any loop in this circuit, it'll pass through two and only two resistors. So all these resistors are in parallel with one another, and they all share the same voltage V. Now, if I define the individual currents, I1, I2, up to I sub n, and then do KCL at this node, I find that I is equal to I1, which is V over R1, plus I2, which is V over R2, plus a bunch of other similar terms up to V over Rn. So I can take out the V. This becomes V times 1 over R1 plus 1 over R2 plus a bunch of other terms up to 1 over Rn. Dividing by I and this term, V over I is equal to 1 over R1 plus 1 over R2 plus a bunch of other terms up to 1 over R sub n. V over I just looks like a resistance. So I can redraw this as a single resistor, Req, with the same voltage current relationship if Req is equal to this term, 1 over the inverse of the resistance R1 plus the inverse of R2 plus all the other terms up to the inverse of Rn. So if I set this resistance to this value, the voltage current relationships at these two circuits is going to be the same. What I can't do is rewrite this in the form of a product of resistances divided by a sum of resistances. The math just doesn't work. Finally, let's take a look at some trends for series and parallel resistances. These can be helpful for double checking your calculations to make sure that they make sense. One easy check you can do is that the equivalent resistance of a set of parallel resistances will always be less than the smallest individual resistance. So if we add resistors in parallel, the equivalent resistance goes down. For series combinations, however, that trend reverses. The equivalent resistance of a series combination will always be larger than the highest resistance value in the combination. Adding additional resistors to a series combination increases the equivalent resistance. It's always a good idea to take a look at the results of a calculation with these expectations in mind. It can help you catch a lot of silly mistakes that arise from incorrect calculations. In this example, we want to find the current I provided by this 5-volt source to this parallel combination of a 2.2 kilo ohm and a 4.7 kilo ohm resistor. This circuit, from the standpoint of its terminals, is equivalent to a circuit with a 5-volt source and a current I with a single resistance Req. If Req is, according to our parallel resistance formula, the product of the two resistances, so 4.7 kilo ohms times 2.2 kilo ohms, divided by the sum of the two resistances, 4.7 kilo ohms plus 2.2 kilo ohms. This turns out to be about 1.5 kilo ohms. So if Req is 1.5 kilo ohms, I is equal to 5 volts over Req, which turns out to be about 3.3 milliamps. So let's wire up this circuit and see if we get the current that we expect. This is my 2.2 kilo ohm resistor. This is my 6.8 kilo ohm resistor. I'm using the analog discovery to apply power to the parallel combination. This DMM is measuring the current into the parallel combination of resistors. If I turn on power and apply 5 volts to this combination, the DMM tells me I've got about 3 milliamps of current, which is pretty close to my prediction. Series resistors can be used to create voltage dividers. Likewise, parallel resistances can be used to create current dividers. That's the subject of our next video.